Now we move on. Part C asks you to write down all the first order condition. So what is the first order condition? Because your optimization problem only involve equality constraint, so basically you just differentiate your Lagrangian with respect to all the variables. So the variables are x, y, z, mu1, and mu2. Okay? So, and they all equal 0. Then, if you differentiate them one by one, okay, the first one, differentiate with respect to x. So, you get 2x. And then die, okay? And this, when you differentiate with respect to x, die, okay? And then you have only minus mu1 to x minus 1. And then minus, well, then no x, so die, and equal to 0. And the others, okay, let me do one more, slowly review the next one. Differential with respect to y, die, okay? So the middle term becomes 2y, minus mu1, and then 2y, minus mu2 times 1, equals 0. The rest, I'm going to do it quickly. The next one is 1, and then, then no set here, so the entire term died, and then minus mu2, and that times minus 1 equals 0. And then differentiate with respect to mu1. Well, this way is easier because this really just give you, this two really just give you the corresponding constraint equation. So let me just copy down the constraint equation directly. So that will give me the constraints, okay? This constraint. This system equation collectively is called first order condition. Now we come to the last part, the most complicated part, that is actually solving this system equation. 5 equation, 5 unknown. But this is really a lie, because if I label this equation by, well, let's say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Basically, one of the equation already tell you one of the variable, because by the third equation, we have mu2 really it's just minus 1. Okay, so mu2 can be read off directly from one of the equation. So five variable, one of them is killed already. Okay, one of them is resolved already. So 4 left. Okay, so if after we resolve for mu2, so at least I can simplify the second equation. Because the second equation becomes what? Becomes 2y minus mu1 2y and then plus 1 equals 0. But you realize that we have learned one technique from calculus 3. That is, whenever it's possible, make x and y in terms of the Lagrange multiplier. So in this case, you realize that you can make y in terms of mu1. So if you rearrange, okay, and I will let you to check, it turns out y equals to 1 over 2 times mu1 minus 1. Okay? And then after you do this, then you want to make x also in terms of the Lagrange multiplier. And you can do this by using equation 1, because by using 1, okay, rearranging, okay, let me say rearrange, you can also make x in terms of the Lagrange multiplier. I will let you to check. It turns out x equals to mu1 over mu1 minus 1. Okay, so please check this. But this utilized one of our technique, so just in case. So we use a different color. If possible, make xy in terms of the Lagrange multiplier. Okay, this is the technique that we are using, and we learned this technique in calculus 3. Okay, so now we have find x and y in terms of the Lagrange multiplier, and then because of the fourth equation, the constraint, we can solve for mu. So put this into the fourth equation. Then what do we have? We have x minus 1, so we have mu1 over mu1 minus 1 and the minus 1 whole square. Sorry, let me use a smaller 1 square. And then plus y square. What is y? Y is this guy, 1 over 2 mu1 minus 1 square equals to 5. And then from this, you realize that you get an equation purely in mu1. So if you simplify this, you realize that this case actually you can simplify this because you will end up having 5 over 4 mu1 minus 1 square equals to 5. So that means that mu1 minus 1 square equals to 1 over 4. And then therefore, there are two possibilities for mu1. Mu1 either equals to a half or 3 over 2. Okay? So, we have two possibilities. If mu1 is a half, then what is x? Because I know, well, x is here. X is here. X is mu1 over mu1 minus 1. So x will be half over half minus 1. So it's minus 1. And whereas y, okay, y equals to this. So this equals 1 over 2 times mu1 half minus 1. So this also minus 1. And how about z? Well, from the last constraint, this equation, we know that y equals z. So if y is minus 1, z is also minus 1. This is by the fifth equation. So from this, we obtained the first set of solution. And then the other set of solution comes from the second case where mu1 is 3 over 2. And I will let you check. In this case, x equals 3, y equals to 1, and z equals to y, so also equal to 1. Okay, please check. And hence, we obtain two collection of critical points. So good critical points the critical points are x, y, or z, mu1, mu2. So the first set is given here. Okay, given here. So we get minus 1, minus 1, minus 1. Mu1 is half. Where's mu2? Mu2 is here. Mu2 is minus 1. Okay? Or the other point is, well, given here, which is given by 3, 1, 1, 3 over 2, and minus 1. And then if you evaluate this critical point in your objective function, what's the objective function? The objective function is x squared plus y squared plus z. So, in this case, f, okay, at the f of minus 1, minus 1, minus 1 equals to x squared plus y squared plus z, so this 1. And then the other one is 3, 1, 1. And that will give me x squared plus y squared plus z, so 9 plus 1 plus 1, 11. Then you have two special values. And which one is the maximum? Of course, it's the larger one. So this one. So let me write it on the step right. Hence, the maximum value, f max, equals to 11. Okay? And indeed, because this is a question about equality constraint only, therefore the smallest one is the minimum value. So note. f min equal 1. So the other value is the minimum value, the smaller one is the minimum value. But this complete, okay, the process of how to do optimization problem using the new language that we introduced here. The new thing really involved is what it means by Lagrangian, and also you need to make sure you check the NCDQ, so NDCQ, to make sure there are no degenerate point. But apart from that, everything that we do are really identical to what we did in the past, okay? Except in the new language. And after we use this new language, in the next video, in the next lecture, I'm going to tell you how we can use this language to approach optimization problems with inequality constraint. So please look forward.